Hey, welcome back to our video series on full waveform inversion by model extension, or FWIME. Today we're going to focus on the first part, theory and design. And more specifically, we saw in the previous video how we constructed our objective function. We introduced two features, first the data correcting term, and then the annihilating term. In this presentation, we're going to explain the role of the data fitting term in FWIME and how we compute it. If you haven't seen our previous videos, we would like to introduce ourselves. This picture was taken in our office at Stanford University. My friend Ettore on the left is from Genoa in Italy, and I am from Nice, France. Ettore and I have collaborated throughout the majority of our PhD lives, and we are really excited to present our work. Also, if you're interested in watching more videos and accessing regular updates on our work, please visit and subscribe to our YouTube channel called EG Optimization. Okay, recall that in the previous section, we showed that the FWIME objective function could be expressed by the following equation. We said that we added a data correcting term g of mi in order to match the observed data as accurately as we wish. And now, as we said, the focus of this video is to explain how this data correcting term g of mi can be computed. Remember, by construction, this data correcting term g of mi should satisfy the following expression. The right side of this equation corresponds to the conventional FWI data residual. They include all the events in the observed data that our prediction f of mi was not able to match because of the inaccuracy of our velocity model mi. And this is exactly what we want our data correcting term to capture. So the question now is, can we compute such a g, and does it even exist? Before we go any further on how to compute g of mi, we need to first introduce a few concepts, and we begin by conventional migration. It is a linear mapping from the data space that outputs an image or a perturbation, p, representing the various interfaces between rock layers in the subsurface. And this migration operator b star is the adjoint of the board modeling operator b. In fact, the adjoint process of migration is also called demigration or board modeling. It is the mapping of an image or perturbation into the data space via the operator b. The third concept I would like to introduce is extended migration or extended imaging. In a similar fashion as conventional migration, it maps seismic data, but this time to an extended image or an extended perturbation p tilde via the operator b tilde star. In a 2D world, this extended perturbation will become a three-dimensional hypercube where the third axis is the extended axis. In order to make this concept a little less abstract, one example of such extension could simply be a pre-stack image for which the stacking over shots has not been applied yet. Indeed, there are many more types of extensions, and we will discuss the ones that we find most useful for our FWIME workflow in a few slides. Note that here the tilde symbol will be used to refer to extended operators or extended variables, and indeed the star symbol is used to characterize the adjoint operators. And finally, if we take the adjoint process of extended migration, we obtain extended demigration or extended board modeling. This process maps an extended perturbation p tilde into some seismic data via the operator b tilde. Now note that both modeling and extended modeling operators share the same output space, which is the data space. Intuitively, in extended modeling, by increasing the dimension of the input space, that is by adding an additional axis to the image, we are hoping that our extended demigration operator b tilde will be able to better capture and predict more complex types of waveforms in the data space than conventional demigration. In mathematical terms, we are designing a new operator b tilde whose rank is greater than the one of b. Here, I really want to stress the fact that b and b tilde are linear operators with respect to p and p tilde, but these two operators depend non-linearly on the same background velocity model mi used to migrate the data and demigrate the images. Also recall that the pair extended migration extended modeling is the key underlying tool behind Ettore's redatuming technique, which is also presented in the target-oriented elastic full waveform inversion video, also available on our YouTube channel. Now let's look at a quick review of the different possible extensions that might be useful for us. As explained by Yang 2013, extended images provide a straightforward way to analyze the image quality and to characterize the velocity model accuracy. There are multiple possible extensions, and here we're going to start by the one referred to as time lags or time extension. Time lag extended images are pre-stack images computed by applying time shifts to the conventional cross-correlation imaging condition. Paul Sava, Sergey Fomin, and Biondo Biondi have successfully developed this approach here at Stanford. The second extension I want to mention is called subsurface offsets or subsurface space lags. Such images are also referred to as pre-stack and are computed by applying a spatial shift during the conventional cross-correlation imaging condition. Images extended with these space lags combined with a differential semblance optimization operator have been widely and successfully used in the industry as a migration velocity analysis tool. That is, to recover the low wave number components of the velocity model. The third extension corresponds to a different and maybe more natural way of examining migrated images. These extended images are not computed directly by applying some cross-correlation imaging condition. Instead, Paul Sava, Sergey Fomin, and Biondo Biondi proposed a mapping that takes time lags or space lags extended images and outputs an image as a function of subsurface reflection angle. The main applications of this technique include MVA and also amplitude versus angle analysis, referred to as AVA. More recently, my colleague Ettore, along with his co-authors Biondo Biondi and Mark Meadows, have successfully used this mapping to illustrate the potential of their method at preserving accurate AVA responses through extended least squares migration. Finally, for the shot record extension, the extended images are analogous to pre-stack shot record migrated images. As explained in Hyung et al. 2016, this extension is used in various advanced inversion techniques and can be computationally less intensive than time or space lag extension. In FWIME, we will present results using either time lags denoted by tau and measured in seconds, or alternatively, we will use the subsurface offset extension, where we will restrict our space lags to exclusively horizontal shifts. We denote them by h subscript x, and we measure them in kilometers. Okay, so we had to make a little detour, but now we have acquired all the necessary tools and knowledge to successfully construct the data correcting term g of mi, which is what we originally wanted to compute. So using what we have learned, we're going to choose to represent g of mi as the application of our Born extended modeling operator b tilde onto some unknown extended perturbation p tilde. Here, notice two things. First, g depends nonlinearly on the velocity model mi via the operator b tilde. However, g of mi depends linearly on the extended perturbation p tilde. And since we're going to consider a 2D world throughout this presentation, p tilde will be represented as a three-dimensional hypercube shown here on the slide. Now that we have made our design choice for g, we can rewrite the data fitting term of the FWIME objective function. And here, we just replace g by b tilde p tilde. Also, since g is linear with respect to p tilde, a sufficient condition to annihilate g is to directly annihilate p tilde. Hence, we replace the task of computing g of mi by the task of computing p tilde. By design, we picked g as b tilde p tilde. Moreover, b tilde, the extended Born modeling operator, is known, which means that we know how to apply it to any extended perturbation p tilde. So the only unknown here is p tilde. And indeed, to compute such p tilde, we use the fact that the data correcting term was originally designed to predict all the events in the observed data that were missed by f of mi. So the way we're going to compute p tilde is by transforming this equality into an inverse problem. And among all the possible extended perturbations p tilde that exist, we're going to choose the one that minimizes this new secondary objective function. Now let's take a closer look at the different terms involved in this objective function. So first, we have our Born extended modeling operator, b tilde. Then we have our unknown variable, p tilde. And finally, we have our data misfit that we want to match. And note that throughout the computation of p tilde optimal, this term stays constant. I want to spend more time analyzing this minimization problem. The first point to notice is that for a fixed background velocity model mi, this objective function is quadratic with respect to p tilde. However, this also means that its minimizer, p tilde opt, depends non-linearly on mi. This in turn implies that every time our velocity model mi changes, p tilde optimal must also be recomputed. So here you can see that we have embedded a quadratic minimization problem inside our main FWIME optimization scheme. To gain better insight on what this new embedded minimization is, let's take a look at what this objective function would look like if we did not use extended operators and extended variables. Say b tilde became b, and p tilde became p. And now this objective function looks very familiar. We have our conventional Born modeling operator b and our conventional non-extended image or perturbation p. We also have some data that we wish to match. Hence, in the non-extended case, this minimization problem would be nothing else than conventional least squares RTM. But in our case, we have an extended least squares RTM, also called extended linear waveform inversion. And the take-home message here is that our optimal extended perturbation p tilde opt is computed in a similar fashion as an extended least squares migration. And we will see that naturally it possesses similar features as extended migrated images. The step in which we compute p tilde opt accounts for more than 99% of the total FWIME computational cost. It is performed iteratively by applying a linear conjugate gradient algorithm. So as you can see, this step is clearly the computational bottleneck of FWIME. Hence, it is worth investing time and effort to investigate ways to speed up this process, especially for our 3D field data applications. Moreover, Hu and Symes in 2015 proposed a very clever way to reduce the computational cost of a similar problem by more than an order of magnitude. Last year, we began adapting their solution to compute p tilde opt in the case of FWIME, and we obtained very promising results. However, we have not had the time since then to investigate this further. This will be our next focus as we move to 3D. The last point is the most important one. That is, by using an extended perturbation, this correcting term actually works under some non-restrictive conditions that I will explain later in this presentation. In other words, once we have found the optimal perturbation p tilde opt, we can predict any of the features present in the observed data that were missed by f of mi. And what is extremely powerful is that this can be achieved no matter how inaccurate or no matter how far your velocity model mi is from the true model. Indeed, this does not work if our operators and perturbations are not extended. The computational of p tilde opt is referred to as the variable projection step in FWIME. The variable projection method was first introduced by Golob and Pereira in 1973, and since then, many authors propose to use this technique to minimize nonlinear optimization problems in seismic imaging. In FWIME, we decided to use this method by following the footsteps of Hyung and Symes 2015. And now we go back to our objective function, and we can replace p tilde by p tilde opt. I really want to stress the fact that in FWIME, only p tilde or p tilde opt is extended. Our velocity model mi, which is the only unknown we want to recover eventually, is never extended. In fact, p tilde opt does not really interest us. It is simply a tool that is going to help the inversion guide our velocity model to the global minimum. Moreover, if we want to be perfectly rigorous, p tilde opt should also be written explicitly as a function of the velocity model mi. However, for the sake of notation compactness in the following, we will not write this dependency explicitly. Now we're going to compute and examine p tilde opt on a numerical example using the well-known Marmoussy-2 model. This figure shows the true Marmoussy-2 model from which we generate a synthetic noise-free dataset recorded at the surface and composed of approximately 200 shots. We use an acoustic isotropic two-way wave equation engine to model the data, and here we display one representative shot gather from this dataset. Next, we consider an inaccurate initial velocity model shown in the top left panel on the screen. The velocity values are laterally invariant and linearly increasing with depth. Then we generate the equivalent data set and we display the analogous shot gather on the left. For this example, we can already see that the initial prediction f of mi is missing most of the events present in the observed data due to the inaccuracy of the initial model. And now we're going to compute via the variable projection step of FWIME the optimal extended perturbation p tilde opt, as well as the data correcting term b tilde p tilde opt. And we're going to see that if we sum f of mi, which corresponds to the dataset shown on the left panel, with the correcting term b tilde p tilde opt, the output will match the observed data almost perfectly. Before we look at this data matching, we need to closely examine p tilde opt computed for this numerical example. And remember, p tilde opt was computed here with the inaccurate initial velocity model mi shown in the previous slide. To illustrate the difference between the two types of extension we use in FWIME, we're going to compute p tilde opt in two different ways. First, with horizontal subsurface offset, and in a separate experiment with time lags extensions. Here, the two different computations are done independently in an effort to illustrate the different properties and features of each extension. And for FWIME, it is crucial and very informative to look closely at p tilde opt. In a similar fashion as extended images, there are two very common ways to visualize this extended perturbation. First, we can examine what we call the physical cross-section, which is a set of points belonging to p tilde opt whose coordinates on the extended axis are 0. Here, this physical cross-section is shown with the red contours. And this is what the physical cross-section extracted from p tilde opt looks like for the numerical example based on the Marmoussy-2 model we just introduced. As expected, you can see that this section shares great similarities with conventional migrated images. The second very common way to examine p tilde opt is to extract a section called a common image gatherer, or CIG, which corresponds to the set of points of p tilde opt that share a common horizontal position value x. And let's take a look at a common image gatherer extracted at x equals 13 from p tilde opt for our Marmoussy example. This panel on the left shows the common image gatherer extracted at x equals 13 kilometers computed with a horizontal subsurface extension. The vertical axis is depth, and the horizontal axis corresponds to the extended axis. And the second panel on the right is the analogous common image gatherer, but this time for p tilde opt computed with a time lag extension. And again here, remember these two panels were computed separately. One important axis in a common image gatherer is the set of points belonging to the physical cross-section. We call this axis the physical axis, here shown in pink. By observing these two common image gatherers, we can clearly see that p tilde opt possesses similar features as the ones in conventional migrated images. For both subsurface offsets and time lags, we can see some clusters of energy spreading away from the physical axis, especially as we move towards greater depth. These clusters correspond to the mapping of events from the data residuals into the extended space. Moreover, the move out of these events can be interpreted and can bring additional information on the inaccuracies of our velocity model mi. Here, for example, the subsurface offset common image gatherer shows frowning move out, which indicates that our velocity model is too slow. This is also confirmed by the move out of the event circled in green on the time lag common image gatherer shown in the right panel. Indeed, the more inaccurate the velocity model is, the more energy will be spread away from the physical axis. Furthermore, we can clearly see that if we did not use any extension for p tilde opt, we would have lost the information carried by these events located in the extended space, which is in fact what happens in conventional FWI or even in reflection FWI when our model is too far from the true solution. One common question that we are asked is how to select the length of our extended axis. And though we do not have yet an automatic way to select it, we can see that the minimum required length depends on the accuracy of our velocity model. And the more inaccurate the model is, the more extension we will need, thereby increasing the cost of our method. However, as we improve the accuracy of our velocity model throughout the FWIME workflow, we will be able to use less extension and therefore decrease the computational cost of our method. So we have studied p tilde optimal carefully, and now let's examine the data correcting term stemming from it. So we take p tilde opt, we apply our Born extended modeling operator, and we obtain our data correcting term b tilde p tilde opt. Now the question is, does our data correcting term b tilde p tilde opt do a good job at matching the events that were not matched in the observed data by our initial naive prediction f of mi? So this is the sum of f of mi plus the data correcting term b tilde p tilde opt, and we wanted to match the observed data d observed. And this is d observed plotted on the same grayscale. And let me now flip back and forth between the two panels to better compare. We observed a very accurate match that could even be further improved up to numerical precision by iterating longer in the variable projection step. Of course, this quality of data matching is achieved for the entire dataset, that is, for all shots recorded at the surface and with a unique p tilde opt. This numerical example shows the potential of extended modeling. Using a naive velocity model, one can find an extended perturbation that can accurately predict all the nonlinearities in the observed data missed by our physical modeling f of mi. One last point I would like to add in this section is that the power of the extended modeling goes further than just the acoustic case. Say that if we have an acoustic initial velocity model m acoustic known to be totally inaccurate, we have an acoustic isotropic wave equation modeling operator f. We have our acoustic extended Born modeling operator, either in time lags or subsurface offset, the same one as we used in the previous slides, b tilde acoustic. And then we have some observed elastic pressure data, d observed elastic. In this case, we observe from numerical experiment that the FWIME data correcting term also exists and can be computed the same way. That is, f acoustic of m acoustic plus this data correcting term computed the same way as we did for the acoustic case in this presentation. Well, this sum can also match the observed elastic pressure data, even though our wave propagations are computed acoustically and our acoustic velocity model is very inaccurate. So to recap, we started with the conventional FWI objective function. Then we showed the existence of a data correcting term that allows us to control how accurately we wish to fit the observed data, no matter how inaccurate our velocity model is. We also showed that this data correcting term is the mapping of an extended optimal perturbation by an extended Born modeling operator. As we mentioned at the beginning of this presentation, being able to match the observed data with accuracy does not guarantee that our objective function bears no local minima. Now we need to construct and design an annihilating operator that allows us to gradually reduce the contribution of this data correcting term over iterations. And this is the focus of the next video. So going back to the main storyline, we are still in part 1, theory and design. In the last video, we saw how we constructed our objective function. And now we just saw how we computed our data correcting term. Well, in the next video, we're going to show you how we compute this annihilating term. If you're interested in watching more videos and accessing regular updates on our work, please visit and subscribe to our YouTube channel called EG Optimization. Again, we really hope you enjoyed this presentation, and if you have any questions or comments, please do not hesitate to contact us. We will look forward to talking to you further.